In this video, we're going to talk about electrolytes, differentiating between strong and weak electrolytes. We're going to mention non-electrolytes and then talk about soluble versus insoluble ionic compounds and how to determine whether an ionic compound is soluble or insoluble using our solubility rules. So the first part is just to define the term electrolyte. And an electrolyte is going to be a compound that when I put it in aqueous solution, it's going to form ions. So an electrolyte, it forms ions in aqueous solution. Remember, an aqueous solution is a solution with water. So if I put it in water, it separates into ions, it's an electrolyte. Differentiating between strong and weak. A strong electrolyte is something that's going to separate completely into ions. So it's going to dissociate or ionize completely. And I am putting it in quotes. It's actually not completely. There's generally a small amount that doesn't dissociate, but for us, it's going to be completely. So completely in aqueous solution. An example of something that would be a strong electrolyte, we could use sodium bromide. If I was to take sodium bromide and then put it in water, so I'm just putting water above the arrow showing that I'm taking my solid sodium bromide and putting it into water, it's going to separate into sodium ions, which are now aqueous because they're in water, and bromide ions. And notice how my arrow is only going towards products. It's not going in both directions. It's not a reversible reaction. If I was to take sodium bromide, put it in water, all I have is sodium ions and bromide ions. I actually don't have sodium bromide in water because it is a strong electrolyte, right? It's completely dissociating in aqueous solution. Soluble ionic compounds and strong acids are strong electrolytes. I will, in a little bit, come and define soluble ionic compounds. The strong acids, you just really need to memorize them. So we're going to put them here. There's 7 of them. The soluble ionic compounds, we can use our solubility rules to determine, but the strong acids, we do need to memorize. So there's 7 strong acids. And these are going to be HCl, HBr, so hydrochloric acid, hydrobromic acid, and then HI, hydroiodic acid. And then also nitric, sulfuric, perchloric, and chloric. So these you do need to memorize. We will use them more specifically when we get to the acid-base section of this chapter, but it's good to start learning them now, so do memorize these. Weak electrolytes are things that are going to dissociate only partially in aqueous solution. So if we go back up, strong electrolytes dissociate completely. Weak electrolytes are only going to partially dissociate. So weak electrolytes these only partially dissociate in aqueous solution. So an example for us, HF, which is hydrofluoric acid. So hydrofluoric acid in water, so we'll make an aqueous solution of it, is going to ionize into hydrogen ions plus fluoride ions, but then they actually recombine to go back to our molecular structure. So weak electrolytes, these guys are only going to partially dissociate. A beaker of hydrofluoric acid has hydrogen ions actually attached to water, so it would be hydronium ions. And we'll talk more about that in the acid-base section of this chapter. Fluoride ions, and then also HF. Our weak electrolytes are going to be our insoluble ionic compounds. We're saying they're insoluble, but they are actually partially soluble. A small amount of them will actually dissociate, so we are going to classify them as weak. So insoluble ionic compounds and our weak acids. The easiest way to recognize whether an acid is weak or not is to memorize your strong acids. If it's not a strong acid, then it's going to be a weak acid. We could actually add weak bases to this. Many weak bases are going to be molecular. Our strong bases are actually ionic, so you can use the solubility rules to determine them. So insoluble ionic compounds, weak acids, and weak bases. A non-electrolyte is going to be a substance that does not dissociate or ionize to form ions in aqueous solution. Non-electrolytes are going to include covalently bonded compounds, but we do need to exclude our acids and our weak bases. So excluding strong and weak acids and our weak bases. So some beaker drawings for us. If you remember your beaker drawings from 130 or whatever your chemistry past happens to be, this is where we have containers with aqueous solution. So basically there's water in these beakers. And then I'm adding to the first one, I'm going to add my strong electrolyte. We used sodium bromide as our example. In the second one, I'm going to have my weak electrolyte. We used HF. And then in the third one, a non-electrolyte, and let's use glucose. So C6H12O6. So if I was to put sodium bromide in water, because it's a strong electrolyte, all of it is going to separate. And there's one sodium ion for every one bromide. HF, I am going to ionize into hydrogen ions and fluoride ions, but there's also some HF in solution, right? Only part of it is dissociating. It's actually ionizing and then recombining. It's a reversible reaction. And then my non-electrolyte, none of it's separating. So C6H12O6. And then of course they all have water in them. So my strong electrolyte, our weak electrolyte, and the non. So I want to go through some examples of ionic compounds and using our solubility rules to determine if they're soluble or insoluble. So examples using the solubility rules, and these are on our periodic table. So if you haven't grabbed it yet, I would hit pause, go get your periodic table, and then come back and resume. You do need those rules to be able to do this. So using the solubility rules, on the back of our periodic table, if you don't know where your copy is, I do have one posted on Canvas, so you can just print a new copy or bring it up on a different device. So using the solubility rules on the back of our periodic table, determine if the following are soluble or insoluble. So our soluble ones are going to be ones that are strong electrolytes. They're going to dissociate completely in aqueous solution. Our insoluble ones, while they do dissociate a small amount, they are weak electrolytes. We're generally going to consider them staying as a solid. So the first one, in fact, I'll just write a whole bunch down and then we'll flip to a periodic table. I have one here we can bring up. So ammonium hydroxide, let's look at calcium hydroxide, magnesium carbonate, potassium permanganate. Remember, all these polyatomic ions are ones that you need to have memorized. And then silver chloride. So I'm going to flip to our periodic table. So let me start with a clean version here. So our first one was ammonium hydroxide. So both the cation and the anion do not need to be on the list, just one or the other, and then we need to make sure that the other one isn't an exception. So for ammonium hydroxide, I have ammonium on my list. So things that contain ammonium are generally soluble. This is our soluble side of our table. I don't have any exceptions listed, so ammonium hydroxide would be soluble in aqueous solution. It would separate into ammonium ions, so NH4+, and then OH-. The second one I have on the list is calcium hydroxide. So what I would do is kind of scan through the soluble side, see if you see any of those. If you don't, then we'll go over to the insoluble side. And I don't have a place here for calcium hydroxide. I do have calcium down in 4, but that pertains to sulfate. And we're not talking about sulfate, we're talking about calcium hydroxide. So going over to my insoluble side, rule number 7 is for hydroxide ions. Again, this is my insoluble side. So things that have hydroxide in them are generally insoluble, but this one does have some exceptions. So group 1A, ammonium, like our first example, and then calcium is listed as an exception. So calcium hydroxide would also be considered soluble. If I put it in water, it's going to dissociate into calcium 2+ and 2 hydroxide ions. Our next one on the list was magnesium carbonate, and the same sort of idea, just see if you can find magnesium on here, see if you can find carbonate on here, make sure that you're not dealing with an exception. So when I look, I find carbonate. So things that have carbonate in them are generally insoluble. I do have some exceptions, so group 1A, so sodium, potassium, all of those, and ammonium are soluble. And I gave us magnesium carbonate. Magnesium is not an exception, so magnesium carbonate would be insoluble. The next one we were looking at was potassium permanganate, and potassium is a group 1A ion. If you see a group 1A ion, it's cation, it's going to be soluble. There really isn't any exceptions to that. So if you see sodium, potassium, lithium, cesium, we don't even care what it's with. There's no exceptions to this one. So lithium ions, right? Sodium ions, potassium ions, and cesium ions. If you see any of those in your ionic compound, it's soluble. One more, and that's silver chloride. And I do have a rule for chloride. So things that have chloride in them are generally soluble. We're on the soluble side of this table. But there are exceptions, and silver is one of them. So when silver is combined with chloride or bromide or iodide, it is then going to be insoluble. So going back to our problem here, we had ammonium on our list. This thing was soluble. We could write an AQ after it because it would be aqueous. Calcium hydroxide is also soluble. Things that had hydroxide in it tended to be insoluble, but calcium was an exception to that, so aqueous. Magnesium carbonate we said was insoluble. Carbonate is on our insoluble side of our solubility rules. Magnesium is not one of its exceptions, so this one gets an S for solid. Be really careful. A lot of times soluble you think S, but the S means solid. So the things that are soluble get an AQ for being dissociated in aqueous solution. The things that are insoluble are going to get an S for solid. Potassium, if you see a group 1A cation, it is going to be soluble, so AQ. Oops. Soluble. And then silver chloride, it was insoluble. Chloride ions are on our list, but silver was an exception to it, so these ones get an S for solid.